meter. So they located about 100 meter from the shoreline. When tsunami comes from the seaside, you can see initially the tsunami hits to the coastal forest, and the height of the tsunami and the energy associated with the tsunami is dissipated when it is passed to this coastal forest. Therefore, this will be a environmental friendly and economical solution to protect from tsunami. Not only finest trees, we found some other species at the eastern coastline of Sri Lanka. They are also very effective in protecting from tsunami. This picture shows the aerial view of one coastal forest located at Batiklo site. So the length of the coastal forest was about 1 kilometer, and here the average width was about 100 meter. So during the field survey, we collected some information. The information such as type of vegetation, tree characteristics such as breast height, diameter at breast height, tree height and tree density. Then forest characteristics such as forest length, forest width, gap between two trees at shore and cross shore directions, and length from the sea to the coastal forest. And also we got the GPS location at each and every forest. So this picture shows the example for the coastal forest. This is forest length, forest width, gap between two forests in shore and cross shore directions. Here tree height. This is tsunami direction. So after collecting all the data, we did some numerical calculation. Here this one, cumulative drag force, that is equal to drag force on one tree multiplied by number of trees per 1 meter width. And here this is the equation we used to calculate the cumulative drag force. Then second, vegetation, vertical vegetation structure, CD all, that is equal to alpha beta into CD. Alpha beta are constant and CD is drag coefficient. Then DNU, effective vegetation thickness, is equal to alpha beta dn dash. Alpha beta are same constants. D is the diameter of trees at best height, and N is number of trees at 1 meter width. And finally DNU, vegetation thickness per unit area, that is equal alpha beta D divided by L square. Here L is the average space between trees. So after doing this calculation, we did some analysis part also. So during the field survey, we encountered many types of species, but out of that we selected 10 different species. Those are very capable of reducing tsunami damage. And I think you can identify some of the trees here. You can see the vertical structure of these trees according to a scale. So these trees, the reason for selecting these species are they are very common in the investigated sites, and also we talk with the people living in that area, and they also prefer for these species to plant at coastal areas. So we analyze the variation of drag CD all with tsunami height for different species we selected, and you can see the variation. For most of the trees, the CD or drag coefficient is equal to 1, but some of the species has large CD value. So if the CD value is large, then we can say that that type of species is more effective against tsunami. But the other thing is, you can here is the lower part of the tree, the CD is very much close to 1 it is, but when it is going up, the CD value is increasing. So that is because of branches. From this graph, we can say that CD is greater for trees with larger leaf density areas, comparatively larger crown area, and including aerial root structures. This species has lesser CD all because of absence of branches. And finally, we can say that some species, the CD value is relatively equal to 1 because of there are branches from the beginning. Here this shows the variation of DNU with tsunami height. You can see there is a large variation of DNU. Here also some species has large DNU value. So when we analyze this graph, we can see that when the tsunami height is less than 6 meter, some particular species are capable of reducing tsunami damage, and when the tsunami height is less than 6 meter, some other species are capable of reducing tsunami damage. So we can see that if we can combine this set of species and this other species, we can get better protection from tsunami. Therefore, there's another concept, combination of vegetation. So here we will introduce the combination of vegetation. We propose two sets of vegetation. This Flaberifer is planted with pandanus in the front line and the Malilcara extendra at the back side in set 1. In set 2, Casuarina and pandanus is planted at the front line and indica is planted at the third line. So you can see here proposed vegetation layouts. In set 1, front line pandanus, then second line Flaberifer, and third line you can see Exandra. In the second set you can see in front line pandanus and second line Casuarina and third line indica. So I have some conclusions. So drag characteristics of different vegetation species were analyzed based on CTOL, DNU and DNOL. We can see that results reveal that trees which have larger leaf area density, comparatively larger crown area and possess area root structures provide comparatively greater CTOL values. And finally, we can say that combined vegetation system is more effective than single vegetation system. Therefore, the present vegetation situation at the investigated sites we can improve by introducing combined vegetation system. Thank you very much for your attention.